workload is higher than other labs, because these are very important stuff. And I received really good comments from last semester. I taught this one last semester as well. So I got really good comments from students. I think this is a good way to go. So if you don't like it, it's your issue. Okay. I will try my best to help you guys throughout all the labs. Make sure you enjoy it. You have to enjoy in order to learn the most from it. Okay. So the feedback from the people were mostly like it's heavy load, but they learn a lot, having fun, and some of the comments saying I should do more cadence tutorials or reduce 1 or 2 labs, which I wouldn't. So the cadence tutorials will start from the end of October. Okay, after we finish all the open source ones, you'll start with the industry standard cadence tutorials. So let me explain why we have to do open source. One of the reasons is that supporting cadence, we just have to appreciate that, because the college is spending $9,000 every 2 years to purchase a license and host it in my server. So it's very expensive to a lot of institutions. And I hired one student, my sabbatical last year in Colorado School of Mines, and they don't have cadence in their department, so I have to hire him to work for me in the summer here, and I was trying to do a senior sum with him over there this fall as well at the same time. But the thing is, their department wouldn't do that for the students, so they don't have cadence, and they won't have cadence in the future. So we have to appreciate that the college is supporting us for the industry standard tools for the students. And I think CU Boulder has cadence, but they dropped it. They just installed Synopsys, and just one professor teaching that. CSU is even not doing anything. So I think we should really leverage this resource on campus. But the thing is, are we going to keep having cadence in the future? I don't know. So we have to keep using the open source tools. So you can see the bottom layers of every transistor structure from the open source tools. Second, in the future, when you are trying to simulate some of the circuits by yourself, you don't have to pay $4,500 a year, and no one will pay that personally. So you can still just directly download these open source tools and make the connections between these two, electro-VSI and LT-Spice, and then you can still do layouts by yourself. It's a really sweet thing to work on. And also open source tools for the first 8 labs, and you'll learn a lot of the fundamental layers, and which are not really visible in Cadence. So you have to sign NDAs. I'm going to send you guys the NDAs from Cadence and TSMC later this week. So they are IPs of the company, and you are not able to see the details of it. But for open source tools, you can see every single thing about it, all the layers in there. So it's really, really nice for students as an undergraduate course. So we are going to start the first lab this Tuesday. It's going to be a DAC. It's a digital to analog converter, but it's a model. It's not really real circuits in there. It's the ideal DAC. So you download all the blocks in your software. So we have to spend most of the time on making the connection between electro-VSI and LT-Spice. So we have to do that first, and then do the simulation. It's really fast lab. It's not really too much work, but mainly a configuration of the tools, right? Okay. So we'll cover a short lecture at the very beginning of the lab, so make sure you are not late for that. Okay, so I'm going to explain how this is getting simulated. So find out the basic RC circuit is very important for digital chips, because it involves all the time delay with the chips, and you are doing most of the time for the chip design is just a timing analysis, just timing, all about time. So for the structure of the course, we have one textbook, and 70% quizzes, homework assignments, and lab reports. And most of them are, so the homework assignments are, some of them are submitted on Canvas, some of them are hard copies. Quizzes are hard copies. and we are going to have sometimes 2 quizzes a week, sometimes 1 quiz a week, so you can do well in the exams. Make sure everybody's on their toes. And lab reports are all of them are digital, so you submit it to Canvas. We have a midterm, have a project, have a final exam. This project will be in Cadence, so expect some large scale circuit being laid out in Cadence at the end of the semester. Okay. All right, so this is required because most of the course materials are from this textbook. This is my PhD advisor. He wrote a book, but he just retired last year from UNLV. And he also worked for Micron on a lot of the memory circuit design, and I think some of the DRAMs in your smartphone from his patents. He has like over 200 patents. And he's IEEE fellow, one of the 2 in UNLV. And one of the students graduated 2 years ago, whose name is Seth Van Mature, I think. So Seth, he graduated 2 years ago and got a job in Micron for DRAM integrated circuit testing in Boise, Idaho. And he was sent to Taiwan for 3 months to bring the fab from Taiwan back to the U.S. So Micron started in the U.S., right? But because of the fab which makes the chips, it's getting expensive. So they moved everything overseas to Taiwan. So they only have a very small fab in Boise, and they have a testing center, have a design center in Boise. So he was hired to that center, but because of the new administration, they want to bring everything back to the U.S. That's why he was sent to Taiwan to learn how to build a new fab in the U.S. back in the U.S. All right. However, if they ship everything back to the U.S., it's being tariffed at 80%. He was complaining, why this makes sense? I don't know either. It's not making sense to anyone. So but he's learning, and I actually met with him in Taichung a week ago. We went to a hot pot, Japanese hot pot. That was fun, a lot of fun. Have a student overseas, and when joining a conference, can see him, which is great. One comment from him, so he felt that doing circuit design is too complicated, is too much work, and he enjoyed the PCB design when he was here with me and with Dr. Joanna Casey a lot. So he prefers PCB design. So the thing about embedded system design is the development period is shorter than IC design. So IC design usually requires a team. Couple people in back end, couple people in the front end, and then work together, and then eventually get a chip. For testing, you need another team. For embedded systems, just yourself, you get the sensors, get the microcontrollers on the PCB, you lay it out, solder it, test it, it's done, it's a product, you can sell it. So it's just more fun, right, because it's a shorter duration. Just FYI. And now let's come back to the contents for today, and I think we have a quiz on Wednesday, so you need to know how to do circuit analysis on the Thevenins, because we need the Thevenins to do the superposition, even though it's the basics, but we still need to go through that, right? Very quickly, for for resistor circuit like this, could you tell me what the equivalent circuit is? I said VE.
It'd be R3 in parallel with R2 plus L1.
So you have to find RTH first, right?
Yeah.
So you are talking about RTH.
Yeah.
So what is RTH? RTH is like you I don't have a load, so you don't have to remove the load first. There's no load, but you are looking backwards. Like you're looking backwards, this is getting shorted. So one quick question, just a sanity check. So why the voltage source is getting shorted always when you are doing like equivalent circuit analysis? Why you want to short voltage source and an open current source? It could be interview questions. Just let you guys know. So ideally, the voltage sources have a zero internal resistance, but current source has an infinite internal resistance.
Yeah.
Okay. So in that case, we can treat this guy as a wire. Just looking at the resistor network. So looking backwards, they are getting that's still the same circuit. R3, R2, R1, right? Looking backwards is R3 plus R1 in parallel with R2.
Yeah.
Okay? Cool. What about VTH? VTH is when you, after you remove the load, the voltage appears at the output, right? At the terminal. What is it?
Maybe the voltage over R2 picture is.
So first, what is this circuit? It's a voltage divider.
Yeah.
So the thing is, there's no current running through this branch because it's disconnected. So there's no current. So the voltage here will be the same voltage at this point.
Yeah.
Agree with that? Because there's no current, no voltage drop, no drop, right? So VTH. So you just need to get the voltage here. And this is the voltage divider, all right? So VTH equals Vn times R2 over R1 plus R2. How do we get this equation, voltage divider equation? How did we get that? R1, R2, and here's the VL, for example. Here's Vin. Around here, 0 volts. It's the same current, right? So assuming that the current is I, so you have VL, which is I flowing through this resistor and times R2. That's VL. Over Vin. Vin is the current times the entire resistance. So this is I times R2 over I times R1 plus R2, right? And I is getting canceled. So that's why VL equals Vin times R2 over R1 plus R2. Am I losing anyone? It's getting recorded. Don't worry about that. It's just, you can always review that. So the one tip to perform well in this class is watch the videos. It's recorded and being uploaded. And especially when you see there's a quiz scheduled on Wednesday, right? So today and Tuesday, you want to go back and watch the video and make sure you can do this. Okay? It's uploaded. So everything's all there. Since you know the voltage divider theory like this, and you know that this is basically voltage divider, and so you can get VTH at this point, like this, and there's no voltage drop, so VTH is VTH, the same voltage. So you can draw the Thevenin equivalent circuit as a VTH being put here, and RTH being placed here, and with the terminal output. Very quick question for you guys. R1, R2, R3. What's the voltage here? Can we use the voltage divider theory? Everything, hey, it's dividing. R2 is dividing. So we can easily apply this equation. This equation. Okay, so VL equals what?
Vn times R1 over R1 plus R2.
R2, right? Because it's a drop here.
Yes, R2 over R1 plus R2.
And this will be incorrect. Why?
Because of
It's taking current from this node.
yeah.
So this and this, they don't have the same current anymore. Here, I can cancel I because they have the same current.
Yeah.
Okay, I can cancel the I. But here I cannot. So I cannot use this as a voltage divider. Okay, just keep in mind.
Maybe you just do R2 and
You have to combine these two first.
Yeah.
Okay. Spice in the kitchen. It's a simulation program for integrated circuit emphasis. Why I know that? Because a professor 10 years ago put this question on the exam. R1, R2, R3, and they are all 1K resistors. VI is a 5 volts voltage. Can I write a spice code of it? The reason we need that is for all the simulation, in electrical VLSI for layouts, we're all using spice. So we need to understand how to code the circuit. It's way easier than software coding anything else, right? There's no algorithm. It's just nodes, locations. Very simple. So don't worry about that too much. So first you label the nodes. How many nodes do you have in the circuit? How many nodes? 3, yes. So 1, 2, and 3 is 0 actually. So we don't have to label 0. We just use it as 0. That's a tradition in SPICE. And keep in mind in SPICE, when you start each line of the SPICE code, if you put a V, if you name the component as starting with the V, it's getting recognized as voltage. If you put R in front of it, it's getting recognized as a resistor. If you put C in front of it, it's getting recognized as a capacitor. If you put an L in front of it, it's being recognized as what? It's a question. It's being recognized as what? L. Inductor, yes. Okay. Great. So now we can name it, but it doesn't matter what are the letters following that first letter. It could be VI, could be V Durango, V's anything, doesn't matter, as long as it starts with V in SPICE. So let's call it V1, it's better. V1, okay, V1. You type, directly type, doesn't matter, lowercase, uppercase, is always recognize the V, okay? V1. V1, so for voltage source, you are putting in the order as the voltage drop. So it's dropping from 1 to 0, right? So put a 1 here and 0 here. And 5 volts. It could be, you could put a 5V or just put a 5. The default unit is volts. And then R, so it's being recognized as resistor, so R1. And R1 is connecting to 1 and 2, these two nodes. All right, and it's 1K. No space in the middle, no space. And then R2 is 220, and it's 1K. And R3 is 220 is 1K as well. So after that, you want to give a command for the simulation run. For example, I want to just do a time domain analysis. I can do dot tran. It's a transient analysis. It's dot tran, no space in the middle. Dot tran. You can do a start time, end time, and the duration between the 2 points. So which means resolution. So if I just do this, I don't put any units after it. So I'm doing 0 to 1 second, and every 0.001 second, I'm plotting a point. So it's going to be a time domain for a 1 second analysis. It will be a straight line, because all these are static DC circuits. So a straight line will plot the voltage. You can plot the current. You can plot power. It's going to be just straight line everywhere, right? Or you can do AC analysis. You can do DC analysis, and sometimes you can change the function, which is the one we are going to use a lot in our labs or in this class, which is called the pulse function. Okay, pulse function. So that's a voltage source actually. you grab a voltage source, you right click and change it to pulse. Because it's giving a voltage pulse, a series of pulses. Why we need that? Because these pulses are basically digital signals, right? Digital 1 and zeros, and that's our stimuli for the circuits. Okay, so we use pulses as stimuli for the circuits. And the arguments inside the pulse are required for you guys. You need to know every single argument inside. So this is, for example, I put a 0, 5 space in the middle. It's starting with 0 volts and then shoot to 5 volts. And there's a time delay. So which means when you want this to happen. So when you want this one, the pulses to happen. So you can put a time delay in front of it. And after that is a rising edge. It's a time, okay? Rising edge. And falling edge. And on time. And period. So these are all the arguments in a certain order. You have to follow the order to when you are trying to modify all the arguments inside. So falling edge, rising edge, falling edge as a digital signal, if you zoom in, right? So the point here and point here won't be instantaneous. There will be a time. It's impossible to have 2 points at the same time point. So there will be a time no matter how fast that is. So this will be the rising time, right? It will be the rising time, this is the falling time, or the falling edge. And you will have a low and then goes to high. So from here to here, that's one period. That's one period. So that's the on time. You just need to define the on time. You don't have to put a downtime or off time for as argument, because if you know the rising and falling edges, the on time, the period, you definitely know that. It's just a subtraction from the total period, right? So a lot of times in the past, the older version of the LT Spice, they wouldn't allow you to put, for example, we don't have to mention that. We just need just let you guys know you want to have a 50% duty cycle for most of the time. So duty cycle means the percentage of the time of the on time taking for the whole period. If you have equal on and off times, this is 50% duty cycle, right? If you have this might be 30%, because the on time here is only 30% of the entire period. That's called duty cycle. So for our system, the digital systems we are trying to use as a stimuli for the circuits is usually we use 50% duty cycle for the pulse function.
And then for the period again, is that when you go across like two writing edges? Or
It's just one.
just
You see
side?
one rising edge, because this rising edge belongs to the next period.
Okay.
So it's starting with the rising edge and falling edge, and then yeah.
Like right before it hits the next
Yeah.
rising edge?
Yeah.
Okay.
Mhm. Now let's talk about superposition. Superposition. So that's one of the most useful circuit laws I've been using for my whole career, even though it's probably you don't have a lot of practice in circuit one. It's just one of the circuit laws you have learned, right? But it turns out to be the most useful one for during practice. So if there's a circuit looks like this, R1, R2, V1, V2. To get V out, There are a lot of ways to do it. Okay, a lot of ways to do it. However, for superposition, we apply one voltage source at a time, and we short the other one. So let's say V1 only. So circuit becomes this. And the other one getting shorted to ground because that's a zero internal resistance for the ideal voltage source. So I2, R1. And this becomes a voltage divider, like what we just did. And you can get a VL1 equals V1 times R2 over R1 plus R2. And for V2 only, we short this guy and got a resistor here, and V2 only applied. V2 R2 R1 VO2 equals
V2 times R1 over R2 plus R1.
Yep. So VO in total equals VO1 plus VO2, which is V1 R2 over R1 plus R2 plus V2 times R1 over R1 plus R2. Okay, that's superposition. Can be applied to many different circuits, and we're going to use this one for the DAC circuit. It's the R2R DAC circuit, and you'll see that circuit in the lab on Tuesday, and also there will be a quiz for the calculation for the using superposition and Thevenins for that DAC on Friday. Keep in mind, since it's recorded, make sure you study this. Okay. Another thing is time delay for RC circuit. So, do you know that for the traces of the circuit, it doesn't matter it's on the chip on the PCB board. You have all the traces, right? You have all the wires, or it could be the pins between the chips. Okay, so it's basically a metal, and you have dielectric material in the middle. So this is forming capacitors. They're called parasitic capacitors. Parasitic capacitors, like parasites, but just everywhere. Parasitic capacitors. So, and also the wires are metal, but they're not ideal. They're not superconductors. They're not ideal metals. They have resistance. So when you are injecting currents or driving a certain circuit, you got R's and C's. They are either in series, in parallel. Doesn't matter. But eventually, you can conclude everything to a model, which is a fundamental RC circuit. Now I get to know, this is why we learned this in circuit 1. Everything comes to make sense, makes a lot of sense. So you got an R, you got a C, you got a V. Let's say this is V, just call it V for now. And I think we did, several different models for this RC circuit, but eventually there's just one equation, and we just change it to different conditions for 3 different conclusions. So this can conclude like 2 weeks of lectures in circuit 1, just to let you guys know, and it's very, very important. So if we add a switch here, and we close the switch at T0, you hate it, right? Why you guys always play with the switch? So childish. Why is there just always someone playing with the switch in the textbook? You hate it, right? But after you notice it's useful, it's making sense, it's just so exciting. Yeah. I hated it when I was in college, but now I understand why. It's great. So in general, for the digital circuits, we are not assuming any initial voltage being stored at the capacitor. So the capacitor, you can imagine from the name, it's cap, right? It's has a capacity. It's actually storing charges. So capacitor stores charges. And for this model, even though we don't want charges to be stored in the capacitor, but it does store charges. This can be treated as a model for all the parasitic resistance and capacitors of the digital circuits, either on the PCB or in the chip, like this. So eventually you got a model like this. And whenever it's getting closed, the switch is getting closed, it's actually mimicking a 0 to 1 jump of the digital signal, right? There's no one like flipping this over there 24 hours, 24/7. But it's just a digital, it's a crystal, right? Crystal is oscillating. So whenever it turns on, getting turned on, it's actually like a switch being switched on. So getting charges being dumped into the cap. So it's getting charged up. So whenever it's getting charged up, you look at VL, this is V in. If you look at VL, it's getting charged up. And eventually, can this voltage here reach V in?
Depending on the capacitor.
I mean, depending on your life expectancy, I think. I mean, the charge time can be super long, right? But eventually, I'm saying eventually, it will be charged up to the full voltage of the input, no doubt. And eventually, there will be no current going through the resistor. Okay? But in digital circuits, this happens in nanoseconds. But I'm saying if you want to make the worst case, it could be a it's a huge resistor to limit the current, to make the current tiny, and you have a huge cap, similar to like ocean size of a cap, but you are using a straw to dumping water into it. It takes like thousands of years, right? But eventually it will be filled up. So, and there won't be any current going through the resistor because they have the same voltage. Same voltage, no drop. There won't be any pressure going either to the left or right. So eventually we'll go up. However, it takes time. Depending on the size of the resistor and size of the capacitor, it takes time. So that is why it's getting so complicated in chip design, because you have delays everywhere. You have to do timing analysis. People spend so much time on cadence because 80% of the time is doing timing analysis. You send a clock from the input, and you are expecting the 1 millimeter away from the input, you are expecting a signal over there, right? And you have like 0.5 millimeter here. You want the pulse reach these 2 points at the same time. So it's having issues. They have different distance, which means different resistance, and will give you a different time delay actually. So you have to insert buffers to delay this one, to delay this shorter one to make it longer. Can you shorter this one? No, because it's right over there. So you can make this longer so they can match, right? So you have to do all these kind of things in the chip design. That's a whole workflow, and that takes like 80% of the time in the whole workflow when people are designing the CPUs over here. I just inserting buffers. So if you get a job, it's actually 80% of the time you are inserting buffers as an Apple digital chip engineer. So that's why superconductors are super exciting, because there won't be any resistance. So you can get a chip designed in a day, right? Okay. Because of time delay, and we have all the things. We have college, we have the courses, we have all these kind of things because of time delay. If there's no time delay, I will lose my job. Thank you. So because of time delay, this is the input, for example, V in, and here's VL. And it will reach the same voltage level, but it takes time. So that's how that looks. How do we know? How do we know it looks like this, not something else? Not like this, or this. Why?
It's not the equation.
It's equation, yes.
Yes.
Yeah. Let's see how that works.
It's
Yeah.
like E did something.
Yes. Great. Good memory. Yeah. So when you close a switch, there are different conditions, right? But not too many, because we don't have 3 components. How many conditions you can have? Not too many. So we can assume that there is a VC0, okay? initial voltage being stored in the cap before we close the switch. But it shouldn't happen in digital circuits because we have oscillation, we charge and discharge. When you discharge everything actually. So we shouldn't expect any charge. But I mean, let's just have a general condition here, a general case, and we read a equation. And so because we know it will eventually reach this voltage at the capacitor, so we know that this voltage can be written as V this, or VC this, right? VC infinity. Because the capacitor's voltage will be, for infinite amount of time, will be this voltage. Okay? So we can denote this as a VC infinite. And one more question. So, for example, this is 5 volts step. Okay? And what if we have 6 volts initially stored in the cap? And we close the switch, what's going to happen? Yeah, current will go to the left, right? Because the higher voltage will... And then what? Then what? After that,
Current will switch back.
It'll go until your cap reaches 5 volts, or once they equal.
yeah, once it's equal, there won't be any current flowing. Yes, and because this guy have a finite amount of charges, it's a floating cap. There's no support after it. It just have whatever stored in the cap, right? So it's going to discharge and then it's gone. You're not getting more into it. So having these two numbers, we can write the equation. It's not a place to derive everything. So this guy, so we what we want to know is actually the voltage here, right? So it's basically VCT. It's a VC in terms of T. That's what we want to know, okay? Well, that's what we want to solve. So the VCT, which is the voltage at the output over time, and that equals this guy plus VC0 minus VC infinite times e to the minus t over RC. That's how this getting derived from. No, this is how we use it. We're not going to derive it. So this one is the equation we want to use. So when we have VC0, like case 1, VC0 is not 0. VC at T0 is not 0, which means the voltage, it has an initial voltage stored in there. And you have to use this equation to solve for VCT, okay? Which is the most boring part. And a lot of people couldn't even memorize the equation. Because that's why you hate it, because it's so long, right? I had to put on a cheat sheet for the exam. So the second case, which is VC is 0. So that's actually the case in digital circuits, because previously it got discharged. So that's why I stored a 0 in there and we charge it up. So it's basically like this, charging up. What's going to happen? You're having VCT equals what? VC infinite minus VC infinite times e to the minus t over RC. And further, it's VC infinite 1 minus e to the minus t over RC. Okay? Some of you are familiar with this equation, right? Because this is the one we are going to use a lot in this class, and this is basically the fundamental physics of the digital circuits. So what we want to do is find out define the time delay of the digital circuits from this equation. So we define the time delay as 50% of the voltage level and from the input and output, and we got a delta t over here. That's a time delay. It's just definition, okay? It's 50% of the input and output. If it's 5 volts, it's going to be 2.5 volts, and it's going to be 2.5 volts here as well. But you look at the 2.5 volts, what the time is the signal at. So then you find the delta t, and that delta t can be calculated. It's a constant. I'm going to show you how. Okay. So now we have this equation. VCT equals VC infinite this will be on the quiz, right? Not this part, but the conclusion. Just pay attention to this. 5 more minutes. So because we know that time delay is being defined as, since we have a t here, so time delay is defined as a 50% of the voltage. So it's basically whenever VCT equals half of VC infinite, right? When VCT reaches half. So this can be cancelled. So ET minus C over RC becomes 0.5. That's great, it's a constant. So now we can calculate T. You are saying, hey, it's a delta T, it's not just one T. We're assuming this is time 0, right? At time 0, we close the switch. So it's basically T minus 0. So this T over here is basically T minus 0 is delta T. So the result will be delta T. Then we do a natural log on both sides. And this becomes and you can use a calculator to calculate this, but it's going to be minus 0.7. So T or delta T equals what? Okay, so it's constant. Okay, I'm gonna quiz you on this a lot this semester. You have to know this. Okay, it could be on the interview. So time delay of the RC circuit is 0.7 RC. Everyone should know that.
So with the DC infinities, the reason why you put that there is because that's where you want to see where the voltage is at that time, or like whenever you make like your substitution from V to T to V to infinity.
You mean here or here?
On the right side.
Here?
Yeah. So.
Yeah, this was derived from here, right? As a special condition when there was no initial charges stored in the capacitor. And so we plug into this equation derived in circuit 1.
Yeah.
And then we find out this guy,
Okay.
VC infinity here, and then we came back here as the same equation. So this one, VC infinity, because we know, like what I said, right?
Yeah.
Given a super long time, you will be charged up. So VC infinity will be the input voltage.
Yeah.
Okay, so it's 5 volts logic is gonna be 5 volts. So VCT is the output.
Yeah.
It's changing over time. So whenever this guy reaches 0.5 of the whole level of the entire input, we write it down here, and the T at this point minus 0 will be delta T. And we want to write it that way because we can cancel this on both sides of the equation.
Okay, so I guess that's my confusion. So why did you make the infinity from T to infinity on the left hand side?
From T to infinity, yes, because VC infinity is actually given.
Okay.
Because after a long time, we know VC infinity will be the input voltage,
Okay.
which is basically 5 volts here, right?
Yeah.
Yeah. Because this is VCT, right? This is VCT, this is output. VC is changing. It's charging up the cap.
Yeah.
The voltage of the cap is changing over time.
Yeah.
So it's charging up, okay? So we define the time delay between the input and output is you pick up the 50% of the voltage level and you look at the time on the x-axis. You pick up y and then look at the x. So that time point will be the time you are looking at, the delayed time you are looking at.
Yeah.
And so that's why we know this is a constant. So when VCT is this changing value equals given one and half of that one, we know the T will be that T we want.
Okay.
Good question. Yeah. Okay. Now you got this cancelled. So T becomes this exactly on the x-axis, right? This will be the T. That T being calculated from this, and minus 0 is basically delta T. So you can get 0.0 RC for time delay for the digital circuits. Any question on anything? Okay? We'll see you tomorrow in the morning, lab.
Brain